Welcome to the Deep Dive. Today, we're tackling something really crucial if you're running Rails applications at scale.
Yeah, it's all about making the most of your server's power, isn't it?
Exactly. We're zeroing in on optimizing that application performance, trying to handle, increasing demands smoothly.
And we've got part 2 of a really interesting blog series on scaling Rails. Today, our focus is, well, quite specific.
Yeah.
How do we actually figure out the ideal number of threads for each Rails process, to get the biggest possible speed boost?
Right, because just throwing more servers at the problem, well, it's not always the smartest move. Or the cheapest.
Definitely not.
So we want to help you understand how to use the resources you've already got, but more intelligently. This deep dive should give you a clearer path without getting totally bogged down in super technical jargon.
And the core concept we're leaning on here is something called Amdahl's law.
Okay. Sounds a bit academic.
It can sound that way, yeah, but it gives you this really insightful framework for understanding the limits, the theoretical limits anyway, of speeding things up by doing tasks in parallel.
So it helps manage expectations about parallelization.
Precisely. It really forces you to think about that split in your application. Some parts can run at the same time, others just have to happen one after another.
Your baking analogy from before, mixing ingredients versus setting the oven.
Exactly that. Some things parallelize, some are just serial.
Okay, so let's bring this back to the source material. The blog post talks about tuning Puma. That's a common Rails web server, right?
Yeah, very popular. And it mentions 2 main settings you tweak: the number of processes and the number of threads per process.
We kind of touched on processes before, so today it's all about digging into that second one, threads per process.
And this is exactly where Amdahl's law comes straight into play. The article uses this helpful analogy. Think of your app's total runtime.
Okay.
It's made of 2 chunks, a serial part, let's call it T1,
Okay.
and a part you can parallelize, T2.
All right, T1 happens sequentially. T2 can potentially run faster with more workers.
Exactly. So when we add more threads, that's the enhancement here. We're trying to shrink T2 down to, say, T2 prime.
Makes sense.
But here's the kicker. T1, that serial part, it doesn't change at all, no matter how many threads you throw at it.
Ah, okay, so that's like the bottleneck. You can speed up the rest, but you always hit that T1 wall eventually.
You got it. It fundamentally limits how much faster the whole thing can possibly get.
And Amdahl's law puts a number on that limit.
Basically, yeah. The law states, let me get the phrasing right, the theoretical speedup gained from parallelization is directly determined by the fraction of sequential code in the program.
So that T1 part, the sequential fraction, is what dictates the maximum possible speedup.
That's the essence of it. It puts a ceiling on your gains from threading alone.
Okay, so mapping this onto a typical Rails app, usually falls into T1, the sequential stuff, and T2, the parallelizable bit.
Well, thinking about how a web request works, the blog points out that the T2 part, the parallelizable stuff, is often the time your application spends waiting on I/O.
I/O, like input-output.
Yeah, input-output. Things like calling out to another service's API, or maybe a payment gateway,
Okay.
or reading a file from S3, like a user's profile picture, or, writing data to your database. These are often things where one thread can wait while another does something else.
Right, they don't necessarily block each other directly. So what's the sequential part then? The T1.
That tends to be the actual Ruby code execution, your business logic, crunching numbers, manipulating data structures inside your app.
And this is where that thing called the GVL comes in.
Yeah.
The global interpreter lock.
Exactly. The GVL is super important here. It comes up all the time in Ruby performance chats.
So can you break down what it is and why it matters so much for Rails threading?
Sure. So think of the GVL as like a single token within each Ruby process.
Okay, 1 token per process.
Right. And only one thread within that entire process can hold that token at any given moment.
And holding the token means?
It means that thread, and only that thread, can actually run Ruby code on the CPU right then.
Ah, so even if I have, say, 10 threads in one process.
Only one of them is actually executing Ruby code at any single instant. The other 9 might be waiting for I/O, or they might be waiting their turn to get the GVL so they can run Ruby code.
Wow, okay. That's a pretty fundamental constraint then when you're thinking about adding more threads within one process.
Absolutely critical. It changes the calculation completely compared to languages without a GVL.
So threads are good for waiting on external things simultaneously, like databases or APIs. But they can't all be running my actual Rails controller logic at the exact same microsecond because of the GVL.
You've got it. And the blog post uses a hypothetical example to show how this plays out with Amdahl's law.
Okay, what's the scenario?
They imagine a Rails app where, let's say, 37% of its time is spent doing I/O, waiting.
So P equal 0.37 in Amdahl's terms.
Yeah.
That's the parallelizable fraction.
Exactly, which means the other 63% of the time is spent actually running Ruby code, the part constrained by the GVL within that process.
Gotcha. And then they show a table, right? What happens is you add threads.
Yeah, it shows the theoretical speedup, S, as you increase threads, N, from 1 up to 8, and it's pretty telling.
Let's hear it. What do the numbers look like?
Okay, so with N1, one thread, speedup is obviously one baseline.
Right.
Add a second thread, N2, and the theoretical speedup jumps to about 1.227. That's a decent bump, like over 22% improvement.
Okay, not bad. What about 3?
And 3 gives you 1.366. So you gained another, roughly 11% on top of the previous step.
Still going up nicely. 4 threads.
With N4, you hit 1.456. That's an additional gain of about 6.6%. Still noticeable.
But I sense a but coming. This sounds like diminishing returns.
Exactly what the blog post highlights. Look past 4 threads. Going to NM5 only gives you about 4.2% more speed up, theoretically.
Yeah.
Then N6 adds about 2.9%, N7 adds 2.0%, and going from 7 to 8 threads, a tiny 1.6% theoretical gain.
Wow, okay. So it really plateaus after about 4 threads in this specific example.
It demonstrates Amdahl's law perfectly. That fixed 63% of serial Ruby execution, limited by the GVL, becomes the dominant factor. You just can't speed that part up with more threads in the same process.
The first few threads help soak up the I/O waiting time effectively.
Right.
But after that, they start tripping over each other trying to get the GVL.
You could put it that way, yeah. The GVL contention and just the fundamental serial nature become the main bottleneck.
And the post makes a crucial point. These are theoretical best-case numbers.
Oh, absolutely. Real world is often messier. Adding too many threads can actually hurt performance.
How so?
Well, each thread uses memory. It takes resources to manage them. Too many threads, and the overhead of just juggling them starts to bite.
Okay.
Plus, more threads actively competing for that single GVL can mean more time spent waiting for the lock and less time doing useful work. It can actually increase latency sometimes.
So just cranking up the thread count isn't a magic fix.
Definitely not a silver bullet.
Yeah.
Which brings up this interesting trade-off they discuss. Balancing threads versus request queuing.
You mean queuing at the load balancer, before the request even hits Puma.
Exactly. So imagine a traffic spike hits your site.
Okay.
If you have more Puma threads ready and waiting, they can potentially grab those incoming requests from the load balancer faster, reduces that initial wait time for the user.
Right, like opening more checkout lanes at a store. Fewer people waiting in the initial line.
Good analogy. But here's the catch. Can your store actually process those customers efficiently once they get to the checkout? If you have too many threads, all fighting for the GVL, your Puma server itself might get overwhelmed trying to process everything it just grabbed.
So the requests get picked up quickly, but they get stuck inside the application server.
Precisely. And the blog makes a really smart point here. In that scenario, it might actually be better for requests to wait a bit longer at the load balancer.
Really? Why is that?
Because load balancers are usually pretty good at managing queues efficiently. It's often less damaging for a request to wait there than for it to hit an application server that's already struggling and potentially make things worse, increasing latency for everyone.
Okay, that makes a lot of sense. Don't pull work in faster than you can actually handle it. Otherwise, you just create a different, possibly worse bottleneck internally.
Exactly. Overwhelming the app server can lead to bigger problems, even instability.
So, following that logic, the blog post advises against just blindly maximizing threads per process. What's the alternative approach?
Their general recommendation is that it's often more effective to scale your capacity by adding more Puma processes.
Scaling horizontally with processes instead of vertically with threads within a single process.
Right, because each process gets its own Ruby interpreter, its own memory space, and crucially, its own GVL.
So multiple processes can run Ruby code truly in parallel on multi-core CPUs.
Exactly. That often gives you much better scaling characteristics for typical Rails apps compared to just piling threads into one process.
Okay, that's a key takeaway. Now, how do you know if you're hitting these limits? The blog mentions monitoring something called request queue time.
Yeah, request queue time. It's a metric that tells you exactly what it sounds like. How long did a request sit waiting before a Puma worker thread even started processing it?
So the time spent between the load balancer receiving it and Puma picking it up.
Precisely. If that time starts climbing consistently, it's a strong signal that your application layer as a whole doesn't have enough capacity for the current load. It tells you requests are backing up,
regardless of the thread configuration details.
Yeah.
A high queue time means you need more overall capacity somehow.
It's a really useful indicator.
And they provide a way to track this. Some middleware.
Yeah, they mentioned Ruby middleware from a service called Scale. It's pretty clever. It uses a standard HTTP header, HTTP request start.
Okay, what does that header do?
A lot of load balancers, like Heroku's routers, for example, automatically add this header. It contains a timestamp of when the request first hit the edge of your infrastructure. The middleware then just compares that timestamp to the time the request actually arrives inside your Rails app. The difference is your queue time.
Simple, but effective. And how do you add this middleware? Is it complicated?
Nope, seems really easy based on the article. Just add one line to your config.application.rb, something like config.middleware.use request queue time middleware.
That's it?
Seems like it. That one line gives you the data to see if requests are queuing up too long, which helps inform whether you need more processes or maybe need to adjust threads or both.
That's really practical advice.
Yeah.
It's also nice that the authors invite people to reach out, LinkedIn, Twitter, their website.
Yeah, it shows they're open to discussion. Scaling isn't always simple. It's often context dependent. An ongoing process.
And they link to their full blog archive, too, for anyone wanting to dive even deeper into Rails scaling topics.
Right. And they mention their company's services, Rails, Dev, React, React Native, and products like Neato and Big Binary Academy. Gives you a sense of where they're coming from.
Okay, so let's try and wrap this up. What's the main message we want people to take away from this deep dive?
I think the core thing is understanding Amdahl's law. Not necessarily the formula, but the concept. It shows that just adding threads in Ruby has diminishing returns because of that serial part, especially with the GVL.
Right. More threads isn't always better and can sometimes be worse.
Exactly. It's not a magic bullet. You hit a ceiling pretty quickly within a single process for CPU-bound Ruby work.
And the more reliable path to scaling, generally,
is often to scale out by adding more processes. This allows true parallel Ruby execution across CPU cores and, crucially, monitor real-world metrics.
Like that request queue time.
Yeah. See what's actually happening in your production environment. Don't just rely on theory.
It really highlights that you need to understand the balance, right? The interplay between tasks that wait, I/O, and tasks that compute, Ruby code. So maybe a final thought for you, the listener. As you think about your own applications with their specific mix of I/O and CPU work, how might you start figuring out that sweet spot between processes and threads? And what metrics, maybe beyond just speed up or queue time, will be the most critical for you to watch in your unique setup?
Yeah. That's the real challenge, isn't it? Applying these ideas to your specific context.